Okay, so welcome to the live session. We are in the week 7 of the NPTEL course Introduction to Electrical Engineering by Professor Bhim Singh. And as you know, I will be your TA for these sessions. So I hope my voice is audible and you are able to see my slides. So welcome to the session. Last week we had a discussion, very brief discussion on induction machines. And today we'll be focusing on another machine, which is synchronous machine, which is another AC machine actually. But the operating principle of the synchronous and the induction machine are fundamentally different. So are you able to hear me and see my slides? Just for your information, we are in the week 11, that is the second last week, and we are going to have some discussion about synchronous machines, right? So if you have some doubt, first let me know that. I think my slides are visible, yes. So we are in the actually week 11, as I told you, and if you have any doubts, just let me know, okay? First let me know if you have, because you have passed a long way, lot of weeks you have just seen the video lectures and have solved the assignments. So if any doubt, feel free to discuss. And we have a live session also on this Saturday and another session, so 2 more sessions. So just feel free to stop me and ask me any doubts you have from the previous assignments or previous lectures. Just feel free to stop me and just ask, okay, if you have any doubts. So now let us proceed with today's session, if you don't have any doubts, and we'll be focusing on some fundamental concepts with which you can solve almost all the problems. So that will be the goal of this session, to discuss all the concepts, all the formulas, related phasor diagrams, MMF diagrams, and working principle, and the way how you solve the problem, so that you can tackle any problem. That is the whole purpose of this live interactive session. And in the meantime, I want you to be interactive, because those who are attending live sessions, they have an opportunity for live discussion and just getting their doubts cleared or concepts cleared, right? So without wasting much time, just let us proceed with the rotating magnetic field. So we already discussed how a rotating magnetic field is generally created. So it is a fictitious field that you generate, fictitious field with even number of poles, right? Why even number? Because I told you, by Gauss's theorem of magnetism, you can just say that magnetic monopoles do not exist. So always they are in pairs, 2, 4, 6, 8, like that. So this rotating magnetic field is a magnetic field maybe comprising of 2 poles, 4 poles, 6 poles, and we saw how to create n number of poles in the stator by the winding. Remember, right, in the previous week. So similarly, the construction of the induction machine stator and the construction of the synchronous machine stator are almost same. That is, we have space displaced coils, space displaced phase coils, which are supplied with time displaced voltages. These time displaced voltages, that means A, B, C, create time displaced MMFs, which in space rotates at a synchronous speed. So the current, the time displaced currents create MMFs which add up to form the rotating magnetic field in space, in actual space. That is, if you sit on the stator and just observe, you will see a fictitious magnet rotating and cutting the conductors. Up to this, the construction is same. So that is how you generate the rotating magnetic field. And just for animation, we have just seen in the previous week also that we have the phasor additions of the MMFs. The currents are creating the fluxes, and then the MMFs just add in space, and its strength is constant with time, not varying. So the magnetic strength is not varying. Obviously, the magnet strength depends on the amplitude of voltages that you supply to the coils, and obviously they are balanced. Balanced positive sequence voltages of a fixed amplitude produces a fixed magnetic strength, that is flux strength. If you change the voltage amplitude, given that it is balanced, then it will add up to be a fixed magnet of a fixed strength for that given amplitude of voltage. So that's how it rotates and cuts the conductor accordingly. The strength of the magnets will just cut the conductors and EMF will be induced of appropriate voltage amount. If you give strong flux, more voltages will be generated. That is, it is induced, I can say, because it is a motor. I am already telling you that I have already given the voltages. Then it will actually create the RMF. But what happens actually, the stator is built to receive or to take the space displaced, that is the time displaced currents through the space displaced coils. But how the current will be generated? So for generators, we always talk about voltage generated. For motors, we talk about some voltages applied at the coils and some motion happening at the rotor. So let's see how the construction is done for synchronous machine, because bus induction machine, what we did, we just placed so this is the principle of locking. Just let us see that and then we'll proceed. So if two magnets are there, they are locked with respect to each other, and then we can generate the locking, and that movement or the rotation is created accordingly. Right, two magnets just locking each other. So that is the philosophy behind the development of synchronous machines. Unlike that in the asynchronous machine, which is the induction machine. So what was the idea? The idea was in induction machine, which was a singly excited machine, what we did, rotor was, let's say, squirrel cage. So rotor was shorted with bars. So that generated a asynchronous torque, which led to the movement of the rotor. Or you generate it over the synchronous speed and it will behave as an induction generator. So the whole purpose was the slip, which was responsible for the generation of EMF and currents in the rotor, which created a magnet, a rotating magnet in the rotor also, which is rotating with respect to the stator with synchronous speed. So that's how we created for the induction machine. But synchronous machine, we follow the locking mechanism. We purposefully place a magnet or some kind of electromagnet in the rotor, unlike that in the induction machine. Induction machine, we don't excite the rotor because it is a singly excited machine. All the power is tapped out from the stator itself. We don't give any power to the rotor because if it is a squirrel cage induction machine. So it is a singly excited. So singly excited machines, we don't excite another coil. In this case, the rotor. But as you know, the synchronous machine, right? We follow the locking mechanism. And it is very important, right? Because two magnets, if locked, then only the rotation will take place. Either rotation will take place because of Lenz's law, or the rotation will take place because of locking. Because you are not rotating the rotor if you are operating it as a motor, right? In a motor, you give the supply. That will generate the RMF. Once the RMF is generated and the locking takes place with the rotor magnet or electromagnet, then on the rotation will happen and it will behave as a motor. Or otherwise, you create an electromagnet in the rotor and just rotate it. Okay, that will do what you see here. That will cut the phase conductors. The phase conductors cutting at different instances of time will lead to the generator of different time displaced voltages in the space displaced coils, which will in turn generate the formation of RMF, and that will lead to the generation of voltages. Or in other words, you can say that fictitiously it creates some RMF, right? So either you create the RMF from the stator and it will pull the rotor with it due to the locking mechanism, or you yourself rotate the rotor, which will form the voltages, just the dual of it. So that was the concept behind the development of a generator, where you rotate yourself with the prime mover. Mechanically, you give power and then you tap electrical power from the stator for a generator or an alternator, how we term it, for a synchronous machine. And for a synchronous motor, you actually give the input, three-phase time displaced balance supply voltages in the space displaced coils. 120-degree space displaced phase coils, and that will lead to the generation of RMF, which will pull the rotor with it due to the locking mechanism. Because rotor is actually an electromagnet. In rotor, you have nothing but a electromagnet. You give the DC and it will behave like a magnet. So simply like that, or a permanent magnet is also used. We call it PMSM or PMSG. Permanent magnet synchronous machine or permanent magnet synchronous motor or generator, however you want to call it. So that was the idea behind the construction, right? So that was how you generated. So seeing the construction of synchronous machine. So we have two types of actually rotors. So one is the cylindrical pole. As you have already seen, I am not stressing upon these points. So cylindrical rotor, another is salient pole rotor. So each has its own advantages and disadvantages. The cylindrical pole rotor, actually, what is that? It is nothing but a cylindrical structure, and that you wound the wires to make it behave like an electromagnet. So among these two shapes of rotor, which one is more symmetric, cylindrical or salient pole? Let's talk about the mechanical perspective first. Let's see where it is used. Which one has more symmetry? Can you tell me? Obviously the cylindrical. And as a mechanical engineer, you should know that if you have a symmetric structure, you can rotate it at high speeds. Because if you have asymmetric structure like this, which is the salient pole, where the saliency is not the same 360 degree. Here it is having more reluctance. Here it is having lesser reluctance, because this axis you have the more iron, right? This axis air. So variable saliency. This is, I am talking electrical engineer's perspective, but from a mechanical engineer's perspective, they don't understand saliency. To him, it is a asymmetric structure. This circle is not fully of iron. So due to the asymmetric structure, if you rotate these kind of structures at high speeds, what will happen? Air will try to come this way, go this way. So air will have to do much effort. And what will it lead to? It will lead to friction, higher friction and windage loss. So more speed you rotate, more the losses. So these kind of structures are usually used in hydro. So salient pole rotors with higher, but it has a advantage. You can embed more number of poles, right? At lower speed. Where you have lower speed, especially in hydro generators, right? Like for example, you see, so 120 F by P, you must know that is the synchronous speed, right? So if you have a higher number of poles, your synchronous speed, if it is grid tied and the frequency is fixed, then the synchronous speed is less. So low speed application, the salient poles are much suited, because in applications where you need higher number of poles, and generally, so this is from an electrical perspective. We can embed more number of poles. It is easier because you have to just stack. You can create more poles like this. Okay. So it is easy to stack more number of poles here. You can create many poles. And in cylindrical, you have to rotate at higher speeds, and poles should be low for that. For a given frequency. These terms I am saying, don't get confused. Can you tell me, if I have a magnet like this, and I have A, B, C in the stator, this is how much pole machine? 2 pole. I rotate it at 1500 RPM. Can you tell me what will be the synchronous speed? Or I rotate it at 400 RPM, let's say. So what will be the synchronous speed? So you apply the formula 120 F by P equal to NS. So F is P NS by 120. So 2 into 400 by 120. That is the frequency, right? But 120 into, yeah. So 120 into 50 by 2. So this is completely wrong. Misconception. These kind of concepts are completely wrong. Because remember, when your machine is not tied to the grid, it is a islanded machine and you are yourself rotating with your hand at 400 RPM, the prime mover. Then if I ask you what will be the synchronous speed, then it will be 400 RPM only. So if the stator is not tied to grid, because what is the difference if you tie to the grid? The grid frequency is constant, 50 Hertz. That will force, so 120 into 50 by 4. So you have to rotate at that speed to synchronize it to the grid. Otherwise, the frequency of voltages induced will be different from that of the grid. And you know you cannot connect two AC sources with different frequency. So if your synchronous machine is tied to the grid, then you have no other option but to rotate at such a speed. You have to synchronize it with the grid, the frequency I am telling. So the speed is fixed. So NS is fixed if machine tied to grid. But if it is not grid tied, if it is an islanded machine, then whatever, for islanded machines, whatever speed you rotate, the prime mover, that becomes the synchronous speed. So in this case, if I tell you that I have a simple machine and I want to rotate it at 100 RPM with 2 poles, then in this equation, if you want to use it, what is the first thing that you will plug in? You have to plug in NS as 100 RPM. Because I told you for islanded synchronous machines, if it is not tied to grid, whatever is the speed of the prime mover, in other words, whatever is the speed of the prime mover with which I am rotating it, that itself is the synchronous speed. That is the speed with which you are cutting the conductors of the stator. And that accordingly the frequency will induce. So what will be the correct answer? 100 equal to 120 into F. F I don't know. F I have to determine by P. So 200 by 120. So accordingly you just calculate some 1.8. Around 1.8. Okay. How much is it coming? 20 by 12? 1.7. Okay. So that is the frequency. So if I rotate at 100 RPM, I have low frequency. If I rotate at 1000 RPM, I get higher frequency. But remember, the synchronous speed is still 100 or 1000 RPM, whatever is the speed of the movement with which I am rotating the prime mover. But what happens for grid-tied machines, either generator or motors, I have no other option but to rotate it at such a speed such that the generated EMFs have a frequency same as that of the grid. Otherwise, you cannot connect them. So that's why we say NS equal to 120 F by P, where you first put F as 50 Hertz for grid and P is 2. Accordingly, they tell you what should be the rotation speed of the prime mover and that you rotate. So there the rotational speed becomes fixed due to the grid. But here you don't have any frequency bound, I can tell. So if someone asks you, I am rotating at 1000 RPM, that is the synchronous speed. If I am rotating at 20 RPM, that is the synchronous speed for a islanded or off-grid alternator. Okay, because alternator you rotate, right? But remember, synchronous motors are always grid tied. Grid means I'm telling the power line, right? They are always connected to the power line. But alternators or generators, like your DG sets, you know, single phase DG sets, you must have seen in shops. Diesel generators, you must have seen small diesel generator sets in shops. Yes. So either they may be single phase or they may be single phase with distributed winding, or you must have three phase for bigger generators. For bigger, you must have seen in some government institutions, in your schools or maybe somewhere, or in the hospitals, you have silent DG sets where you have a small shade and they tell you when the power goes away, then the DG set will take the backup. Inside that, what is there? It is a diesel generator. So that is nothing but a synchronous generator. Okay. So that is not tied to the grid, because when it functions, when the power goes away, so it is islanded. So whatever frequency you rotate, whatever speed you rotate the prime mover, that itself is the synchronous speed. But we generally rotate such that the DG set also generates 50 Hertz. That is a different thing. But you must understand, alternator means synchronous generator, and generally diesel generator sets are also synchronous. Like your train also, you know Rajdhani, right? In Rajdhani, the front and the back, those two bogies, right? They also carry diesel generators for emergency power backups. And where the power comes from the in the other bogies, you know, in railways, where do the coach get the power from? From some battery banks. No, that top electric is only for the where? So you just go and see. There are many interesting things that you will come to know. So first the engines were driven by the coal, burning coal. After that, what came? Diesel engines. Now most of the engines are electric also, right? So that engine is actually electric, or top electricity, the catenary cable that takes the power. Only the engine. But where the lights and the maybe fans, just go and see. They are all DC, 110 volts. You saw, right? DC ports are available, right? And you must have seen all the fans, all the lights. Yes, they are all driven by, as a source, it is driven by batteries. Many batteries are kept at the bottom of the bogie. Just go and see. Each of 2 volts connected in series. No, AC to DC, yes, okay, all those are okay, but where the source, bulk power is coming from in the bogies. So that is actually coming from the battery banks. No, that is for emergency purpose. Actually, the batteries drive them. Just go and see. It is interesting. So there is a complete different architecture of power. You will ask me why. That whatever you are telling, it may be drawing the power from the top. But generally, railways have designed that system that the engine should be fed with the top power line, and that will pull the bogies. But for auxiliary usages, they are actually following the battery banks. So that is more flexible, right? So that's why they are following that topology, right? So anyways, let us go to the equivalent circuit of the alternators, or whatever you call synchronous machine. So let us see what is the equivalent circuit looking like. So you remember in transformers, right? We told that the operation of the induction machine is almost same as that of the transformers. Only the transformers are not rotating and don't have air gap, whereas the induction machines are rotating machines with air gap. Otherwise, they don't have armature reaction. Transformers also don't have armature reaction, but they have air gap. That is the induction machine. and that's why we have more no load currents and all those things we talked about. There is coupling. Coupling is there. There is mutual flux both in the transformer as well as in the synchronous machine, right? As well as in the induction machine. We have coupling. If we don't have coupling, that is the flux getting linked with the other conductors, then how can voltage be induced, right? Whenever voltage is getting induced, those two coils are getting some mutual fluxes, right? For which actually I can say that the voltages are induced in the conductors. So there is some common flux linking the coils. And with time that is also changing. That's why AC voltages you are getting. Okay, that is clear. But please understand that you had kind of a magnetizing branch, which is nothing but the mutual branch denoting the flux linkage mutually from the stator side as well as from the rotor side. That was the whole purpose, right? So this was primary, this was secondary, or this was stator, this was rotor, and this was the branch where the induced EMFs take place. Similarly, let us do it differently, right? In synchronous machines, but in induction, the exciting source, so this was R2, this was R2, 1 minus S by S. Just add these two, it will become R2 by S. So this was induction, right? Where the excitation from only one end, that is you can say stator. But for synchronous machines, you are exciting two ends. The rotor, which is nothing but behaving like a magnet, and the stator. So this rotor will induce some EMF in the stator. And this EMF will pass through series of coil resistance and reactances and lead to the generation of voltages. Now these two circuits are they equivalent? Rotor is not shorted. But produces flux linking stator coils. So this is the stator circuit. And the role of the rotor giving the power or the excitation, what is the power in the rotor? AC or DC for a synchronous machine? No. You are having a battery, a small battery, whose current in the rotor, who decides the rotor current? Just let me ask you a few basic questions. Who decides rotor current? Not in an induction machine, I am telling in a synchronous machine, where you have simply a coil and a DC source. Please note, a DC source. Who decides the rotor current? The resistance of the coil. Simply a resistance of the coil will decide the current. V by R. That current will lead to generation of flux. That flux will cut the conductors in the stator. So rotor handles DC, small DC power. But what is the magic that it is doing? It is cutting the conductors. That will lead to the generation of EMFs in the conductors. Otherwise, rotor is only handling small DC power. We are not drawing it here in this circuit because what is the purpose? This is variable. As you change excitation of the rotor, that DC voltage excitation or the resistance, however you call it, that will fluctuate in the form of variations in the amplitude of induced voltages in the stator. And assuming that the rotor is rotating at synchronous speed. Please understand that in synchronous machines that are tied to the grid, you have no option but to rotate it at synchronous speed, and that will not be going to change. If you have the fixed number of poles, let's say 4 poles, what will be the speed of rotation? (1500 rpm), and this is fixed. You have no option to change it. But if you want to control the power factor, speed is fixed, okay. But if you want to control the power factor, that the stator power factor is degrading, so let's push. See this branch. Let's push more reactive power or reactive currents, so that just KCL. Maybe one angle 90 degree was the angle of the current. If I push, have some mechanism to push or to push some voltages, so that, or in other words, some currents, so that these two currents sum up and this current becomes one angle 0. So this kind of doubly excited nature circuits, where you have where we can actually vary this voltage, this mutual voltage, as well as this voltage, then we can gain control over the power factor for a given load. So if you have some load, maybe powered, so this is a single phase equivalent circuit, right? So this is a 3-phase system, but we are drawing the single phase equivalent circuit. Phase A, phase B, phase C all will be same, like this only. So what I told you, that if I have control over this and I am giving something from this side, like in a motor I tell, I am giving VT, I am also controlling the EF because I have the excitation in my hand. And similarly, I have EF as a generator. I generate some voltages and I power the load. But as the load keeps on changing, I want to also control the power factor. Then I have to vary the, again, the power angle or the EF. So we'll see all the phasor diagrams, don't worry. But please understand, rotor DC, pure DC. Rotor only creating the job of producing some controlled flux. More flux becomes more reactive power. Less flux, lesser reactive power, right? Because it is generating voltage support. No, stator not DC. Stator is AC, right? See, simply if you give some DC battery and supply the rotor, it will lead to DC currents. But those currents will produce flux, like the rotor flux or the field flux in a synchronous machine, cutting the conductors of the synchronous machine. So what a rotating magnet does, it creates what form of voltages in the stator. If you sit on the one coil and this kind of magnet is cutting it while rotating, so when magnet is there, this coil generates maximum EMF. Then it falls, then it like this. So it generates AC voltages. So a DC rotor cutting the conductors of the stator also produces a completely AC sinusoidal voltages. And we can improve it by distributing the coils, right? All those distributed windings you must have learned. Short pitch, long pitch. So all those techniques are there. But rotor handles DC power. And accordingly, for doubly excited machines, you have control over stator power factor for a given load. So what I am telling like this, even if I power some reactive loads, I can control my excitation to ensure that my stator power factor, that is the power factor terminal voltage and stator current, this voltage, this is VT, this is IA, this power factor becomes unity. I can do it. How can I do it? By changing the angle and the magnitude of EF. So I can vary the excitation and accordingly I can push the same amount of power but at a better power factor. That is what is the magic. So I want to transmit the power, but at a better power factor. Why we are always concerned about better power factor? Because for a better power factor, you can transmit the same amount of power for a lesser amount of current. Why you know? See, this is voltage, this is current, and that will result in some power, right? So in phase component of I can be thought as delivering the active component of power. Now, if I had a poor power factor for the same power I want to transfer, then my current would have looked like this, more lagging. Just see, length of current increased for same power transfer. Power transfer for same active power transfer at a poor power factor. So if I have a poor power factor and I want to transfer 100 watts, I have to push more amount of current than that required for pushing the same 100 watt of power, but at unity power factor or better power factor. Understood? Why this is advantageous? To push the required amount of power required by the loads at a better power factor. I told you we can push the same power for a reduced length of current. And why so we are very interested in reduced length of current or minimum current? Because we want to reduce the I square R losses in the stator winding, as well as the heating and failure chances of the winding. So what is better in electrical engineering than to push the required amount of power without heating or with lesser heating? Heating will be there, but with lesser heating. That's why power factor is very important. In transmission lines also, we push the same amount of power with a better power factor. Why? Because the copper losses reduces. Because I told you to transfer or to transmit the same amount of active power, it is better to do it at a better power factor because you reduce the length of the current for the same amount of power factor. And reducing the length of the current to push the same amount of power enhances the maximum power transfer ability at a better power factor. And that reduces your I square R losses in the transmission line. That leads to much efficient power transfer. So as you know, the generators or the alternators in a thermal power station are also connected to GTs, the generator transformers, and then they are passed to the transmission line. So you want to obviously operate the generators at a better power factor, because if you don't do so, then the currents will be large and you almost all the power that you generate or sell to the grid, to the power grid, will be lost in the form of I square R losses. So your end consumers will not pay you for that, right? If you are trying to transfer 100 watts and in the process you lose 200 watts, then who will pay for the additional 100-watt loss? And you will not gain anything out of it. So the business will stop. So business will not run. So power factor control is very important, and that's why as an electrical engineer you learn power factor improvement techniques. All the var compensators, all the things, so much things you learn in power system, like transposition of maybe transmission lines to reduce the inductance, and all forms of things to provide support or to improve the power factor, maybe at the load end or the generation end. All the game that is going on is only to improve the power factor. Power factor is a local thing. At a particular node, we define the power factor, not every point. And locally, you try to improve the power factor, because from that frame of reference, you are actually trying to push the power or enhance the power transfer capability with minimum losses or with minimum length of current, which enhances the power transfer capability. You can push more power, right? If for 100-watt current required only 2 ampere, I can push more power, right? I can generate more power because the conductors will not be burdened, right? So that is the whole concept. I want to sell maximum amount of power, and you can sell only active power, not reactive power, because reactive power looks like what? Positive it goes and then negative it comes back. Unidirectional flow of power is only defined as power in electrical engineering, and that is what we term as active power, which power is actually resulting in the formation of torque, in mechanical systems and resulting as voltages or currents and glowing a lamp or rotating a fan. You are getting the mechanical things or mechanical effects only due to the active power, because reactive power over a cycle, if we see, it comes and goes. So it only it only results in copper losses, because the current component comes and goes and results in I square R, I RMS square R losses only in the line, but that don't result in active power transfer from source to load, because it never goes from source to load. The reactive power, I am telling, only active power generated by a system helps in the power transfer. All these points you please remember, because now we will be drawing the phasor diagram and the MMF diagram, with which you will be able to solve almost all the problems, right? So please stay with me up to this point and I will just impart you the concepts. So a very important thing which we will try to discuss in today's lecture is the first, building the equivalent circuit. I will draw it and trying to derive the condition, trying to derive the power formulas and trying to derive the condition on the load angle as well as the impedance angle. So power factor angle and the impedance angle, right? Impedance angle. So what is actually we are trying to see that at what condition, at what angle my power transfer will be maximum. And in the process, we'll derive the complete formulas for power transfer. So let us just quickly do that. Maybe please take a copy and a pen maybe. So this will be important for you. So we quickly derive the formulas. Okay. So slides are changing, right? Okay. Yes. So what is the model? Single phase equivalent model of a synchronous generator. I told you that we have some voltages induced, EF. So this is the open circuit induced voltage by the rotating field coil or the rotor, which is nothing but electromagnet and induces some voltages. And we have XS, synchronous reactance, and RS, forming ZS. Now this RS is actually the stator coil winding resistance. But what is this XS? We will discuss about this XS sometime later, okay? Just a slide later. But this XS is not as simple as you think it to be, okay? But for the time being, just let's say we model this XS and call it synchronous reactance. What is it? Why it comes? We will see. It has two components also. So this synchronous reactance, we will talk about it after this derivation. But let's say that the coil has some inductance, which we call it the synchronous reactance, right? And then it has the terminal voltage where you connect the loads. Now, generally you plug into the grid also, or the infinite bus. Maybe it powers some load like a diesel generator, or you connect to the grid. Let's say we connect to the grid, right? So then the grid voltage is VT angle 0. Always the grid voltage is taken as reference. Then please remember, to operate as a generator, we'll see all this in the phasor diagrams also. EF should lead VT. We'll also see that. If it is working as a synchronous generator. I'm not talking about the amplitude. Amplitude of EF and VT may be different. All these we will see in the phasor diagram. But just for the time being, please understand that for power to flow from this side to this side, that is, my machine is acting as a generator, because from source to load the power is going, then please remember that wherever the power is going, that angle should be more than wherever the power is going to. So if the angle is 0 degree, I took the reference, the angle delta should be greater than 0 degree for power to flow from generator to load or grid or infinite bus. Understood this concept? This is valid all everywhere in power systems, right? So power systems teaches you this concept that if you are talking about power transfer between two AC sources and I know that my power goes from this side to this side, then for sure, if I have two nodes, VT angle delta 1, VT1 angle delta 1 and VT2 angle delta 2, obviously I have some impedance. And if someone tells you power flows at this side, then for sure delta 1 is greater than delta 2. You can derive this thing and see either through phasor diagram you can see or through, we'll derive that. We'll see in the phasor diagram how it comes, okay? Simple concept. I can tell you why it is so. Just see, if this is VT and this current will be I. So I is lagging in nature. So VT minus IS excess. IS excess because there is an excess and minus IS excess. So reverse. And that will go in forming VT2. So you see, with reference to VT2, VT1 is leading by delta. That is what we call as the power angle between the induced voltage and the VT. So you see, you derived, right, that VT1 angle, that is the angle difference. If this VT we consider as the reference, then you see angle delta, it is leading. So that's why I told this delta 1 should be greater than this delta 2. Okay, understood, for power flow. So now let us derive the condition. The formula on power flow in a synchronous machine, and then let us derive the formula or condition for power transfer, maximum power transfer, right? So are you with me up to this point? Yeah. No. For motor, see, don't think like motor generator. How you connect a motor? A motor draws power from the grid, right? Because motor has to convert electrical energy to mechanical energy. So it should draw power or take or give power to the grid. Just apply common sense. It should draw power or give power. Motor. It should draw power, right? So if it is drawing power and the circuit remains exactly the same, so as per the derivation, what does your common sense tell you? If power is flowing from this side to this side and my this side angle is 0 degree, so what should be the angle of EF? Delta. Delta now should be less than 0 degree for motor. That's why for motor, what will happen? EF lags VT. So these things don't mug up, we'll see in the phasor itself. All the mathematical things, it will fall in place in the phasor diagram and MMF diagram. Once you understand that, there is nothing left in synchronous. Okay, just try to understand that. So up to this, you are with me? Okay, so now let us derive. Okay, so there are some technical notations. I told you we'll discuss about the excess later. Just for the time being, for simplification, this is the single phase equivalent circuit. Just be with me, okay? So we call this RA, armature resistance of one phase coil. So this is a single phase equivalent circuit, how we draw it. And this is the induced voltage in the stator, not rotor, don't confuse. Induced voltage in stator of that phase. This is phase voltage, please remember. So we now have the VT, right? And this is IA, armature current of one phase. So assuming it is working as a generator, can you write the equations for me? EF angle delta minus IA angle, let's say phi, into ZS angle theta, because this is ZS, right? Angle theta. And maybe should be equal to VT angle 0. What we did, EF minus IA ZS, just writing like this, EF minus IA into ZS equal to VT. We can also write like this. Clear, right? So let us draw the phasor diagram, okay? So if I just assume for the time being, this is my VT. Let's say that the IA lags, okay? So just tell me VT plus IARA plus IAJXS will be EF. So VT plus IA into RA, no phase angle change, plus IAJXS, because XS has 90 degree. So always when you are multiplying with some J, multiplication J results in one angle 90 rotation, anti-clockwise, right? As per the rule of multiplication of the complex number. So this generates EF. And the angle between VT and EF is known as delta. And the angle between VT and IA is known as phi, or the power factor angle. And the angle between EF and IA is known as psi. Some notation they give. So for generators, psi equal to phi plus delta, where delta is power angle or load angle, and psi is known as internal power factor angle, which we don't use generally because we are concerned about the angle VT and IA. This is the power factor we tell, load side power factor, right? And the synchronous impedance angle, is theta. So this is the synchronous impedance angle. This angle is theta. Clear this phasor diagram? So either you can do it like this, or we have a formula. By resolving these components, you get a formula, okay? Very easy formula. By resolving these components, then you can solve it directly, or you can use this formula. So what is the formula? See, EF cos phi. Where is EF cos phi? This is EF, this line. EF cos phi means this length. This length is EF cos psi. EF cos psi I am telling, okay? This length. Agreed? This much. From this to this. This EF cos psi. This can also be, I can write it like equal to VT cos phi. Just see the angles, okay? VT cos phi is how much? This much. Plus IARA. What is the advantage? That you are doing the amplitude breakups. So don't have to do any phasor analysis. Angle, you don't have to take any angle. Only you plug in the magnitude of psi, EF, VT, phi, IA, RA. Don't need to bother about vector addition or phasor summation. So you don't have to tackle with your scientific calculator phasor summation. So this formula becomes very helpful for students in the very early stages of learning, where they can resolve and plug in the amplitudes of the parameters and get out the formulas or the parameters. Otherwise, in one line you can write and do complex analysis, complex multiplication and division, and can get the currents or EF. In different problems, they give one set of parameters and they tell us to find maybe VT or EF or IA, like this. You will see one of the problems like that. So horizontal breakup gives me this formula. And what the vertical breakup gives? Vertical breakup also gives similar thing, that EF may be writing here, that EF sine maybe cos phi, so sine phi can be written as this thing equal to IA XS. No J is written because we are only talking about the lengths, just geometry. IA XS, and then what is this? This is VT cos VT sine phi. Agreed, right? Simple. So if this is 1 and this is 2, if you add 1 and 2 by squaring, so 1 square plus 2 square, equation 1 square plus equation 2 square, you do, and you can arrive at a formula that tan psi, you just divide EF square cos square psi plus EF square sine square psi, and you will get like some, resolve it, and you will just derive easily in 2 lines. You can derive that tan psi is VT sine phi plus IA XS by VT cos phi plus IA RA. This formula you will require in some point, right? Accordingly, if you try to find out the power, right? Power derivation. So this was one of the formulas. Power derivation, right? So there is the synchronous reactance and the resistance RS. And this is EF angle delta for a generator. So I can call it ZS angle theta S. Synchronous impedance angle, right? And they generally call it IA angle phi. Not psi, because we are interested about this power factor, and VT angle 0. This is the common notation. So what is the S apparent power? VT into IA conjugate. And you can write IA angle psi can be written as EF angle delta minus VT angle 0 by ZS angle theta S. Agreed or not, this formula? So this you can plug in here. VT angle 0 and EF angle delta, take the difference and divide by ZS angle theta S. You will get the IA. This formula is understood, right? And you take its conjugate. This is phi, yes. Because the power factor angle, this one. The angle between VT, and I took the reference of VT, right? That's why I'm telling phi. So VT has an angle 0. So this angle with reference to VT is obviously phi. With respect to VT, IA is standing at an angle of phi. So I should write phi. I need to take one reference and write all angles in reference of that angle. So as we can see that the angle between VT and IA is phi. That's why I'm writing phi. Now plus phi or minus phi, that the formula will give me. I know that there is some angle phi. Whether it is lagging or leading, mathematics will give me, right? So because I don't yet know, I am trying to find out IA magnitude and phi magnitude. So what is it? EF angle delta minus VT angle 0. These are all known, right? Divided by ZS angle theta S. So that will give me IA angle phi, and then I need to take the conjugate, and I will get the S. The real part of S will give me active power, because S is what? P plus JQ. Up to this it is understood, right? Easy. So if you just put the value of IA into this equation and take the conjugate, Conjugate means you have to just, overall angle, you have to just take the negative of that angle, right? So you'll get the formula as S load VTIA conjugate, which will come out as EF VT. You just note it down, or you will get the material also by ZS theta S minus delta minus VT. This is the angle minus VT square by ZS angle theta S. So this is the formula. And if you try to take out its real part, you will get active power as EF VT by ZS cos theta S minus delta minus VT square by ZS cos theta S. Now, if RS is 0, because in synchronous machine RS is much smaller than XS, so theta S is also 0. Then you will get that P is nothing but EF VT by XS sine delta. This formula will become very simple if RS and theta S are 0. But let us try to find, there are two variables, right? Theta S and delta. That what should be their value so that the power transfer is maximum. Let us see this, okay? So I need another slide. So up to that we derived that what will be the expression in terms of delta and theta S. Now let us see that if we derive and try to find out, so dP by d delta, let's find with respect to delta. So what should be the value of power angle? And theta S we assume not varying, right? So we'll find EF VT by ZS sine of theta minus delta minus 0, because cos theta we assume constant, right? And derivation of constant is, you see the formula, cos theta is constant, right? That's why. So that becomes 0. Derivative of x with respect to 2 is 0, like that. Getting my point, right? And then you try to determine condition over delta. Try to do one by one. There is condition on theta S, there is condition over delta for maximum power transfer. So just try to determine, you will get sine theta minus delta is 0. In other words, theta minus delta is 0, or theta should be equal to delta. This is one point. Now let us derive dP d theta is 0. Or let us put theta equal to delta in the original equation. Like that also you can do. EF VT by ZS cos theta minus delta minus VT square by ZS cos theta S. Here if you put theta equal to delta, then what will you get? That P is EF VT by ZS minus VT square by ZS cos theta S. Now what will be the value of theta S so that this power becomes maximum? Can you tell? There is a negative sign. So I want this term to completely go to 0 so that my power becomes maximum. So cos theta S should be 0. That means theta S should be 90 degree. That means the condition becomes theta equal to delta equal to 90 degree from here. So this is the complete set of condition that your synchronous impedance should be purely, what does it signify? Theta is equal to 90 degree. What does it signify? What is the physical significance of synchronous impedance angle? No, that is okay. Theta is, equal to delta equal to 90, understood that for this condition getting satisfied, you will get maximum power transfer. I am not asking that. I am asking that, okay, understood that for 90-degree power angle, power transfer is maximum. But what is the physical significance of this theta s equal to 90 degree? What is the theta s? Theta s is the angle of synchronous impedance. If theta s is 90 degree, what does it mean? That Zs is purely reactive, no Rs. If it is so, then my power transfer will be maximum. That's why in synchronous machine, Rs is much less than Xs. Understood, right? So let us take another slide, and I want to write down the formula again clearly for you, just for your application completely, right? So formulas, important formulas. After that, this we'll talk about Xs. Okay. Up to this, you are with me, right? My voice and everything is clear, right? Okay. So the important formulas are very easy. Just let me write it down for you. I think my slide is moving, right? No, it is not moving. Okay, yes, it is moving. So for generator, right, the power can be written as EF Vt by Xs sine delta. So just assume Rs or Ra, armature resistance, to be almost zero. So this is a simplified form, right? This is very useful, okay, in all the problems. And Q, reactive power, Vt by Xs into EF cos delta minus Vt. So this is for generator. And for motor also, P as EF Vt by Xs sine delta, and Vt and Q as Vt by Xs EF cos delta minus Vt. Power wise, I am telling. So whatever the generator will generate, that will go to the motor. That is very trivial, right? We are talking about the magnitudes. I think you have noted it down, right? Let's go to the discussion on Xs. I think again, okay, slide is moving. Discussion on some air gap and Xs. So what is Xs? It is a term which we call it synchronous reactance, right? Now it is composed of two terms. One is leakage and one is armature reaction, right? Leakage, you know that once we have air gap, if it is more, then leakage also more. And I told you that leakage we model as inductance, right? Similar to the induction machine. So XAL value also increases. But as your leakage increases, your mutual reduces, linkage reduces, opposition reduces, armature reaction reduces. And please remember, leakage is lesser than armature reaction, because the phenomenon of armature reaction is more severe in doubly excited machine. In induction machine, we were not talking about, but it is very important in synchronous. Because you should understand, there is a field which is cutting the conductor, generating voltages. That voltage is applied at the load, load draws some current. That current creates a flux, armature MMF we tell it, to oppose the main flux. That resultant flux is known as the flux due to the effect of armature reaction. So armature currents create a flux in such a direction, maybe partially opposing or fully opposing, that we will see, and that we can also control. For doubly excited machine, we can control the effect of armature reaction. Or in other words, we can control the effect of power factor. We can control the power factor. Okay. But there is armature reaction. We'll just see the MMF diagrams, how it all happens. But please remember, armature reaction is a dominant phenomenon in synchronous machine. And purposefully, we build more air gap. We talked about this point in previous week. I think you remember. Compared to induction and synchronous, we have little more air gap in the synchronous. Why you can tell? Can you tell from this logic? Reducing coupling, but is it good? Reducing coupling, we talked about it in the induction machine, that purposefully we built lesser air gap so that most of the coupling happens, more EMF gets generated, and then more of the torque we can get, because cutting more flux linking with the rotor in an induction machine generated more coupling and more torque. More flux cutting, more EMF induced in the rotor, more torque, because more current getting induced in the rotor, more torque, right? We got it, we wanted more torque in the induction. But why we are sacrificing with a lesser linkage, slightly lesser linkage, sacrificing some phenomenon in the synchronous? Because it is a doubly excited machine, we can actually generate that loss by building a stronger electromagnet. But we are gaining something in putting more air gap. What is it? I told you that, okay, leakage increases slightly, we can compensate for it by the doubly excited circuit of the rotor, doubly excited circuit of the stator and rotor combined. We can compensate for it. But additionally, one more advantage we are getting. Can you tell me what? By increasing slightly the air gap. Okay, we can compensate for the loss, but some gain is happening. What is that gain? I want to hear that. Some gain is happening. No, the armature reaction reduces. The effect of armature reaction reduces. And once the effect of armature reaction reduces, since I told you that it is a dominant factor, the total excess reduces. The power transfer ability of the synchronous machine enhances. Because excess reduces, power increases. So, power pushing ability or power transfer capability or stability increases. Stability increases. Just learn about the term synchronizing coefficient. It is very easy. Just learn from a good book. You must have also learned by this the dP by d delta I am talking about. So it is also a measure of stability that is enhanced, right? So that is why by the construction we slightly want to reduce the effect of armature reaction. Armature reaction is not desired actually. Okay, we want to reduce its effect, but we cannot help. Armature reaction we completely cannot eliminate. It is there, which has some effect on the net flux, but we want to reduce that phenomenon. But it still is a dominant phenomenon, and that's why we are incorporating that flux, that additional component, by the term XAR, and totally we term it as synchronous, synchronous reactance, right? And in ZS, excess is dominant. So RA is almost desired to be 0 for two things. One thing is to make the loss completely active loss in the stator, active copper loss, it to be almost negligible. And one more thing is that to enhance the power transfer capability. We saw, na, as per the derivation here, that theta S should be 90 degree, purely reactive. Theta S is the synchronizing impedance. That should be purely reactive, means that there should not be any RA, but that is not possible practically, but we want to reduce it. That's why I'm telling excess is dominant. So while drawing the phasor diagram, we'll just play with excess. So now let us come to the important thing that we are discussing. We have 30 more minutes, and maybe we can, no, sorry, we have 50 more, how much? Yes, 40 more minutes, and we can discuss the phasor diagram and armature reaction and some basic problems, right? Which you will be able to solve most of the problems. It is very easy. But this is more important because this is the tool which we will be using for the problem solving. Problems, I have given many problems. I also can give you 10 more problems in the group. But more than problems, these concepts are important because these problems will be these concepts will be helping you solve the problem. If you don't understand these things, the armature reaction, the phasor diagram, the MMF diagram, this 1, 2, and 3, if you don't understand, you are completely lost in synchronous machine. So we'll learn these three and then we'll see the problem and then we'll wrap up, right? So up to this, you are with me, right? Any doubt up to this? Because these three now are the most important tool of synchronous machine, and we'll be starting one by one. So any doubt, just let me know. Otherwise, we'll proceed. Okay. So we just start the phasor diagram, right? So first, the phasor diagram, you need to understand that in phasor diagram, what we do, we try to analyze the effect of variation on one parameter on the other parameters. We want to see something without writing the equations. By plain geometry, we want to visualize some operation of the synchronous machine. That is why synchronous machine, we learn phasor analysis. That is without doing any mathematics, just by the help of geometry, I can tell you a lot of things that is not so trivial to do with mathematics. Understand the purpose? Understood, right? So first understand the purpose. Purpose, without solving complex phasor equations, we can take help of phasors to analyze the effect of variations in one parameter. So one by one we can do. Only one parameter variation is allowed. Multiple parameter variation you cannot analyze geometrically. Only one parameter allowed variation. So now what we allowed? We kept the mechanical power input to the alternator constant, P mech equal to P elec, that is P electrical, by power balance, assuming no losses are there, no loss assumption, which is almost true because RA is almost 0. Then we are varying the excitation. Let us see what happens. So there is a constraint that power is not varying. Let's see what is the effect of variation on EF. I told you, na, EF, angle. Let us see what varying it causes. Varying it means amplitude wise, not the angle. Angle will be decided by KVL. Let's see how we do it. So what you do, you just draw VT, first step, and start with a lagging load. Now what is root 3 VT IA cos phi? It is power. But in phasor we do per phase. So let us see VT, P proportional to VT IA cos phi. But VT is constant for alternator. So P proportional to IA cos phi. But if P is constant, I told you, IA cos phi is constant. So if this angle is phi, this is the constraint line. IA cos phi constant because power is constant. Now tell me, let us assume RA to be 0. Now IA RA VT plus IA RA plus IA excess. So IA excess will be like this, J IA excess. So this is leading to the formation of EF. But you also know P is EF VT by excess sine delta. But VT is constant. So what you do, P is proportional to, because excess is constant, Vt is constant. So P proportional to EF sine delta. And this is delta. So this sine delta means this much. EF sine delta constant. So these two are the constraint lines. So a lagging operating alternator. Now you take it to leading, right? Let us see what happens to EF. Please note that once it was lagging, this EF cos delta was greater than Vt. Please note. Why? Because EF length tip is above Vt. Noted? Yes or no? Please tell me. This is important. So EF cos delta is more in length as per geometry compared to Vt length. Noted, right? That means somehow EF you need to supply more, right? In some sense. So this condition is termed as overexcited. Because if you go back and look at the formula of reactive, active you know, EF Vt by excess sine delta. If you go back and look reactive, Vt by excess EF cos delta minus Vt. So you see, EF cos delta greater than Vt means Q is supplied. Because Q being positive means Q is supplied, right? By the machine to the load. So always remember that a generator feeding a lagging load gives reactive power to load. See, there is no meaning of giving reactive power or taking back reactive power, because I already told you that reactive power comes and goes back in one cycle. But still we term it that lagging load absorb reactive power and leading load deliver reactive power. This is not true. But what is true? In the phase, one reactive power coming and going back for the reactive load, and for the lagging and leading load, they are in 180-degree phase reversal. So this one is for the lagging and this one is for the leading. So that's why we tell when one is absorbing, one is giving. Concept understood, right? There is nothing known as absorb or give, because nothing is going anywhere, because nothing is lost or nothing is gained as per reactive power waveform. But still we tell that if it is 0, let us assume, as per the convention of electrical engineering or power system, we assume that lagging loads absorb reactive power, and that is given by the machine, synchronous machine. You can see that EF cos delta is greater than Vt. That is a overexcited situation. Why overexcited? Because someone is taking money from you. Assume the lagging load is taking reactive power. Then you have to gain more money or supply more money to fulfill their needs, fulfill their excitation requirement. In the term, you can create an analogy that if someone asks you, your friend asks you for 5 rupees, you have to give them 5 rupees. So you have to first have 5 rupees, then only you can give 5 rupees, right? So you have to first generate that 5 rupees, or overexcite yourself, or excite yourself with 5 rupees, or have 5 rupees and then give. If you don't have, how can you give? So since you are losing something, you have to generate more. That is a situation we term as overexcited. We have to provide more excitation or generate more excitation or give more EF to create more flux to give or to provide for the excitation required for the loads additionally. So this situation is known as over-exciting or providing more EF. Understood, right? Now let us see, as per the convention, you have to create some notion that if it is a leading load I told you delivers reactive power. So your friend is giving you money. So you need not again generate more money, right? You can spend it. So that is an under-excited situation. So since you are getting more money, you have to spend it. So you have to lose it. You don't have to generate or gain or increase EF to provide for the reactive power, because increasing EF means providing more reactive power. But you don't need to do so because you are already getting it from the load. So that's why I can draw the phasor diagram. If this is IA, how will be IA axis? Like this. But please remember the tip should stop here, because I have a constraint over EF sine delta, because the power was constant. So EF is like this. EF new. So once load is leading, I saw that EF length also reduced, and now EF cos delta, EF new cos delta new is less than VT. So this is a leading load alternator under excited. So what you learned from the phasor diagram? So leading load and lagging load. Leading load consumes reactive power. Leading load supplies reactive power, and lagging load consume reactive power. So alternator for leading load should be under excited, and lagging load, since it is taking more reactive power, you have to provide more excitation, so should be over excited. Please remember it. Even if you forget, you can quickly draw this small diagram and check that okay, EF is more, crossing the tip, remember, then more EF is required for lagging load. See, for unity power factor load, if IA is like this in phase with VT, then you completely are operating at this point. You see, EF cos delta equal to VT. No extra excitation required for UPF. Neither under nor over. Whatever is given is sufficient. Understood, right? So giving more excitation means taking the generator towards leading operation. If the load is constant, if the load requirement is fulfilled and still you give more excitation, what will happen? Generator will run as overexcited. The power factor will improve. Power factor will be leading and it will degrade. Right? We want unity power factor operation. Neither we want lagging poor power factor, nor we want leading power factor poor. Both are poor case. So we don't want to also give more power, more excitation, so that it drives it to over excitation. We don't want to do it. We only want to give that much what is required, so that the length of the current also reduces. See, here check. For leading as well as lagging, the length of the currents were more. But as soon as you operated in unity power factor, for the same power factor, for the same power transfer, the length of the current was least for the UPF. Accordingly, if you draw the alternator with constant excitation phasor, now the EF is maintained constant. So VT, IA, and VT plus IA excess. So this is JIA excess. Sorry, it will be like this, right? And this will give me EF. But now EF is constant, let's say. So how to draw? You create a circle kind of thing. And now EF is constant, right? Power is not constant. So what can you build? What constraint lines you can set? So power is EF VT by XS sine delta. But now power is varying. So I have no constant on power, input or output power, but I want to maintain EF constant, right? Can you quickly draw what will happen if I maybe try to reduce the power factor? Let's say I operated the, or let's say my EF is now here. Power angle increased. Can you draw what will be IA? New IA. So for that, you need to join the tip of VT and EF. And so this should be VT plus JIA XS. And how should be IA looking? So IA should be 90 degree to it. But now you see IA XS length has also increased. But XS is same. So IA is increased. But how will IA look? Because if IA was like this, IA XS became like this. So if now IA XS is more and like this, how will IA look? See, IA XS line is perpendicular to IA. So it should be like this. IA2. Understood, right? So with same excitation, if we want to go and feed a leading load, then both delta and IA increases. That is, your power angle also increases and your current length also increases, right? Any doubt? Any doubt? Please tell me. So if it was like in middle way, exactly at the tip, then you have minimum current. Then slightly more than this because you kept the excitation constant, right? Because this length is more than this length, and this length is more, much more than all of the three. So since these lengths are increasing, IA is increasing. Hope you get the concept, right? What I am trying to impart. Because this excitation is constant. So IA3, if I turn this, so IA1 length is least, IA3, then IA2. As excitation kept same, and we move from lag to lead. Obviously, the power angle also increased. IA increased. But EF is leading. Wait. Now let us go to the motor. So motor you can draw it, right? Simple. You do the same thing, VT minus IARA So minus JIA excess, right? So this is minus JIA excess. So this is EF. All the conclusions will be just dual of that. Now see, EF is shorter, means EF cos delta. So first observation is EF lags VT for motor, and EF cos delta is less than VT. EF cos delta less than VT means that the excitation is lower, so should be overexcited, because lagging loads consumes, sorry, underexcited. Consume reactive power. And if it is increasing, then we call it a overexcited scenario for leading operation, right? So try to do it as a homework. So understood, right? Here the load is absorbing reactive power, so underexcited. Motor at lag, underexcited. Now motor at lead generates reactive power, so should be losing, it is losing reactive power, so should be overexcited. So EF cos delta less than VT means it is, so this is lagging, right? So just try, okay? Now let us look at the MMF diagram, right? What is MMF diagram? We are analyzing the three MMFs. What are they? One is field, one is armature, one is net. For generator and motor at lag, lead and UPF. How the MMFs magnetize or demagnetize or cross magnetize or change or have an effect on the field, actual field MMF. That is the analysis, that how the armature reaction is playing a role for different loads. Because armature reaction, why is it coming? For the current drawn by the loads. Who decides the current? For an alternator, who is deciding the current magnitude as well as the current angle? Who is deciding that? The load, the connected load. So I am wanting to analyze that for different connected loads, how the behavior is changing for your generator and motor for different loads, lag, lead or UPF. So up to this you are with me, right? So if this is coil A, this is coil A dash, this is B, this is B dash, sorry, this is B, this is C, and this is obviously B dash and C dash. And I told you already that if this is N, this is S, then obviously this coil is like this, maximum voltage will be induced in this coil, as well as maximum current will be induced at the same instance in this coil because they are at UPF, right? So dot and cross. So the field MMF is like this, because field flux north pole, south pole like this, FF. But F armature, you do like this. In a coil, you do like this, right hand rule. The net armature MMF is like this, FAR. So it has neither, since two fluxes are perpendicular, it does not have a net reaction, right? It is called cross magnetizing. And obviously remember that your generated voltage will always lag the MMF, field MMF, by induced by the field MMF by 90 degree. That's why if this is the FF, I can say this is the EF. Sorry, this is lead, I think. I need to lag, so this is the lag. So you can understand it does not demagnetize actually. Neither it completely magnetizes. No portion of it has any component on this. That's why we tell it cross magnetizing, right? Because the magnetic lines are completely perpendicular to each other. When two lines are perpendicular to each other, you learned in vector that they don't actually influence each other completely, but changes the axis of the flux, axis of the net flux. No component of FAR is on FF. Similarly, no component of FF is on FAR. So neither is it aiding FF nor is it opposing FF. So that's why we tell it cross magnetizing kind of. Okay. And now, if you want to see what is for lag, easy. Similarly, voltage is induced here. But where is the current? If the rotation is in this direction, can you tell? Since current is lagging voltage, either by 90 degree or by some, current will go at its peak little later. Agreed, right? So this coil is now getting the maximum EMF. However, current is not maximum here. Current will be maximum at a slightly later part. So where is current maximum now? Current is now maximum here. Some other coils. So this was FF. Now current max. So you do the right hand rule, and this is F armature. So you see, if you resolve it, one part is pulling it down, one part is like this. You resolve it, right? So this is the demagnetizing effect. So a lagging load demagnetizes net FF, and hence I told, we saw in the phasor that alternator powering lagging loads should be overexcited. Means more EF is necessary. Means more excitation is necessary to compensate for that armature reaction, or in other words, for the additional reactive power or excitation requirement by the lagging loads. That means EF should be increased if you want to compensate for that FF drop and still maintain the same induced voltage in the coils. Because why we are doing all this analysis is not only for the reactive power improvement, but also this armature reaction is resulting in XS. You remember XS has two components, yes or no? XAR and X leakage. So also power factor, rather than that, XAR is also significantly affecting this drop. It is leading to drop in voltage. And that drop we don't want, so we need to increase EF. Understood, right? The flavor. Yes. So just remember that for lagging loads, they are taking reactive power, pulling it down. So the excitation of the machine should be increased in order to supplement for that requirement, right? That is what the MMF diagram is also telling us. The current is lagging, and the MMF of the current, which we tell as the armature MMF, armature current MMF, that is pulling the field MMF down, a part of it. But if it is ZPF lag completely, zero power factor lag, then what will happen? Then it will completely try to demagnetize the net field MMF, like it happens in your short circuit condition. What is the load? Load is purely ZPF, because consider RA to be 0. Short circuit pulls the MMF down and hence VT is gone. That is a way of thinking, okay? So that is how it does. Similarly, lead diagram you can do. Just ZPF lead diagram, you will see it has an aiding component. So leading loads magnetize the net FF, hence underexcited. The alternator is underexcited. Since it is already getting the required excitation from the other loads, connected leading loads, that's why we are reducing the excitation of the machine. These are the statements, right? And similarly for motor, please remember that whatever you were doing for the generator, up to the induction part it will be same, but the current will be reversing, because generator provides the current but motor takes the current, right? So let us see one example you will understand. For motor, let us see, right? Cross magnetizing. This will be cross magnetizing, just do and see. But what you need to know, I am just telling you. Let us see lag, okay, for a motor. These are all 120 degree, okay. Induced voltage will be maximum in this coil, agreed. And the rotation direction is like this. So the voltage is maximum here, but current will be maximum already has passed. Current maximum has already passed. That is, this coil has already received the current maximum. That is what leading means. And now which coil is at maximum? The future coil is already at maximum. This is what leading means. Some leading coils are already at maximum. Current is leading, right? So you see for the motor what happens, this is the field MMF, and this you do right hand, this is the armature MMF, and one part of it is like this, another part is aiding. You saw it is aiding or magnetizing part. So motor at lag absorbs reactive power, has magnetizing armature reaction. So it already is receiving the excitation from the power generator. So should be what? Underexcited or overexcited? Already receiving more excitation, so it should be itself underexcited or yes, underexcited. This is how we analyze. If the net MMF is lifted up, then its own excitation should be reduced. That is what we tell as underexcited. So remember, generator, that is alternator operating at lagging power factor, providing the lagging excitation of the loads, should itself be overexcited so that it can power the excitation requirement by the loads. But the loads, which are the lagging motors, synchronous motor operating at lagging power factor, they are receiving the excitation. That's why should be underexcited. That can be validated or justified by the phasor diagram or through the MMF diagram. And they are dual of each other, right? So try for the lead, try at home. And next, we'll just see the numericals. V inverted V curves are nothing. You can just see the V and inverted V curves. I will just write it for you. Whatever we discussed in the phasor diagram, that is summarized in the form of two curves. One is V curve, one is inverted V curve. That tells you the variation of armature current with respect to field current for the V curve, and the inverted V curve, the power factor. The y-axis becomes the power factor. So all the conclusion, what we discussed in the phasor diagram, you can draw and just see. Either two ways. You can remember the V curve, or better you remember the phasor diagram, because in all the numerical, the V curves or inverted V curves will not help you. The phasor diagram only will help you, and the power angle equation and the equivalent circuit, that will only help you. Otherwise, nothing can help you. So V and inverted V curves you can learn yourself, and I have no comments about it because they are not so helpful in solving the numericals. But all the conclusive results that we summarized can be found out from the V and inverted V curve. They are only built to actually make you remember easily all the points we discussed. That is what is varying one thing on another having. So we can just have a look on V and inverted V curve. You can see the lecture also. It is very well explained. And from there you can get an idea, because that is not helpful for the numericals. Okay. And the OC and SC test and sleep tests have already been covered very well in the lectures. That they are very, I told you also that short circuit test, how you do to flow the rated current, just like the transformers. Okay. And sleep test you understand. OC-SC test I know you will understand, but that is for excess, determination of excess unset. But sleep test, do you know? I think they have covered. Professor has covered in the lecture, right? Sleep test, any explanation needed? Then I will ask one question and go to the numericals. If you know sleep test, I will ask one question. Sleep test you know or no, not know? Sleep test is nothing but a variable reluctance path test where you have the alternator 3 coils. You supply with a low voltage. Field coil you open circuit. And you pass the rotor, rotate the rotor at maybe 1400 RPM. And let's say it is a 4-pole machine. So what is the synchronous speed? 1500 RPM. Let's say it is tied to the supply. Low voltage supply. You supply by a variac or auto transformer. Then what will happen? Since the machine RMF, since it is 1500 RPM, 15 Hertz, 50 Hertz, the rotating magnetic field is rotating at 1500 RPM. But the rotor is rotating at 1400 RPM. So if I sit on the rotor, what will I observe the speed of the RMF to be? I am also rotating at 1400, slightly less than synchronous speed. There is a rule. NR should be less than NS. So what should I see? The speed of the RMF. 100 RPM. Like the sleep speed. So what will happen? The voltages that are induced in the field coils will be of sleep frequency. That is agreed, right? Voltage should be induced in the field coils because now, till now, the machine rotor and the RMF were synchronized. That's why the no voltages were induced in the rotor. No AC voltages were induced in the rotor. But now AC voltages will be induced in the field coils. What I was telling this much time, DC, DC, DC. For normal operation, it is DC. But now in this test, I open circuited the field coil. But still, since there is a relative velocity of the RMF with respect to the field coil, there is some sleep voltages, AC voltages induced. This much is agreed, right? Now, another important information is that this rotating MMF is cutting the red conductor or red phase conductor, RYB they generally tell, that is a 3-phase machine, right? At a point, and the voltage is maximum. But this test is generally conducted for salient machines, where the shape of the field pole is like this. So when this is like this, the A phase, since it is already connected to a supply, will draw less current or more current. Can you tell? See how the connection is I am drawing. They are star connected. And I provide the variac with supply AC. So if I connect, stator is shorted, right? A coil. It is a coil, complete connected coil, not shorted, but it is connected end to end. So I provide VR, VY, VB, but of lower magnitude, lower than rated, 20%, 20% of V rated, about 80 volts. If it is 415, I give maybe 80 volts, 83 volts, like that. So now this current, it will draw. Now, based on the reluctance of the flux path, it will draw variable amount of currents, what we call as the no load currents or whatever you want to call it. Okay, so, but this current will be more or less when the rotor will be like this, coming exactly below R. The current drawn by the coil will be more or less. Who defines that current? The reactance path, right? And reactance part is modeled with inductance. So that inductance is what? LD, turn square into permeance. Now turns is not defined because turns, you have to see what is the turns here. Maybe the magnetic path and the number of turns of the coil you have to see. But this permeance is more or less. Less, right? There is lesser air gap. So if I connect a voltage source across the coil, in order to set up that much flux, I connected the voltage source, right? Across this coil, which is connected end to end. To set up the flux, the AC flux in the coil, the reluctance path offered is lower, then it will take less current or more current. So situation is like this. I have a AC source, I have a coil. Now this coil has to generate some flux, and for that it has to take some small current. Now if air gap is more, this reactance becomes less or more? No. See here, formula, permeance. If air gap more, reluctance more, permeance less, inductance less. So if air gap is more, inductance is less, current drawn is more. So I increases as air gap increases. Yes, so current more means this variac drop will be more or less. I more as air gap more, variac drop, that is the drop, small drop happening at the variac, this supply transform. Variac drop is more, right? Because current is more I into small impedance. So this voltage, terminal voltage reduces. So these positions will come many times. So this is what we were talking about. Some drop along the D axis, it is lesser drop, Along Q axis, it is a higher drop in voltage and the more current, right? So slightly lower voltage and more current, and again, based on the slip voltages, it is appearing. The position of the rotor with respect to the coil, it is happening, right? Because there is R, there is X also, but generally it is what I can say. See, one thing you need to understand, that once you have voltages, supply voltages, that supply voltage will power the stator coils. Now that it is simply inductive in nature, but also small resistance is there. So that will decide how much current it will take. But the amplitude of the current that it will take will also be not only dependent on those field coil reactances, but also participated with the reluctance path. So that is having dominantly inductance only, right? But that inductance is varying. Understood, right? Leakage is there, okay, but that leakage path is sometimes getting iron, sometimes getting air. That is, it is varying, right? So its magnitude is varying. XD sometimes, XQ sometimes. So as per one coil, I am seeing, sometimes it is getting more, sometimes it is getting less. So that is the current shift is dependent on the amount of inductance. We are modeling it with this XS, and then we are seeing like this IA. But this value is also changing, right? And there is a small RA also. That's why the current lag or shift, whatever you call, is not constant. Understood, right? But it is almost lagging. Q and D don't have any sense. They are only the direct axis, meaning the pole axis, and the off air axis. They term it like this. You have to define two axes, right? That's why the term named them as D as direct axis and then Q as quadrature axis. Understood, right? So there are some numericals. You just go through the numericals. Just apply phasor analysis. EF angle delta minus IA JIA XS and angle phi equal to VT angle 0. Okay, these will solve all the numericals, right? So just see them, and I will provide you all the. So we already discussed that speed of the shaft decides the synchronous speed for an I not tied to grid, right? We discussed already. And then this is a very interesting problem that came in GATE 2024 based on the formula we already discussed, right? We already discussed this formula, right? Just that phasor diagram you just solve, VT, and then IA, then IA RA. RA you can neglect, JIA XS, and then ER. So this angle is nothing but delta, that is nothing but theta or phi. This they call it psi, and this they call it as theta. This is the triangle you need to resolve, and they have applied like this. Nothing else. This is the formula. So accordingly you can do, and this is a efficiency problem. Just what is efficiency? It is nothing but P out by P in, or you can write as P in minus loss by P in, or you can also write as P out by P out plus P loss. Sorry, P out for a generator. If I tell for motor, input power is what? Output power plus losses. So you can write anything, both for generator or motor. It is true. Motor will have mechanical losses, and because motor will have electrical losses because the input is electrical and output is mechanical. But the generator will have input is mechanical. So input is mechanical means input to output side we are going. Yes. So mechanical, then to electrical. Electrical also loss it will happen. Then total loss we have to add up, and then we can find the efficiency. This is the way, and that is what we have calculated, right? So with this, I think you can solve almost all the problems. Just go through the concepts once again. And if you have any doubt, I will provide you with the solved examples also in this material. And you can just check and let me know, right? If you have any problem. We can also connect at the extra class, extra session we have on Saturday. I request you to join that session also. We have some more problems and discussion, right? So do you have any further doubts? Else we can close the session, right? We are already over time. Okay, thank you. I will provide this. These all are uploaded, right, in the portal. So you will get them. And also I'm sharing in the groups, right? Okay, thank you. You can leave the call. I can end the session here, right?